Hello and welcome back to Calculus 1, section 4.9 on antiderivatives, also known as integrals. So here is where we start our third part of Calculus 1. Part 1 limits, Part 2 derivatives, Part 3 integration. Chapter 5 will have 5 sections. Those 5 sections will be all on integration. So now, what we have is antiderivatives, which means this will be undoing derivatives. And one fact of differentiation is you can differentiate anything. Integrals? No, you cannot integrate every function. And also, some of the integrals are insanely tricky. We have split this into Calc 2. So first half of Calculus 2 will be advanced integration techniques. You are only going to learn basic integration tonight, and then eventually use substitution method in 5.5, which will be crucial for your survival in Calc 2 and your future courses, because most of them are U sub. So the goal for tonight is to understand this. The derivative of x squared is 2x, which means that if I want to undo this operation, I'm going to say integral of 2x dx is equal to x squared. Now there is more to this, but let's come back to it. The derivative of x squared plus 100 is also 2x. And now if I do the integral of 2x dx, I get x squared back just like up there, which is a problem, right? And if I go the derivative of, let's say, x squared minus 6, the derivative is still 2x, and the integral will still be x squared. The problem is that the derivative destroys this information about constants. Therefore, we have to use, when we integrate, we have to use plus c, plus some constant that we don't know what it is unless we have more information to calculate that constant, which will be explained at the end of the section. So now, from this exercise, all of this that you have above compresses into integral of 2x dx is x squared plus c. And that's it. This is considered a formula. Now, obviously, you're not going to memorize this one. You're going to memorize something much better than this. But the idea is that the only thing that you see when you are solving problems is this side. You don't know where this function originated, right? And that's why you don't know if there was nothing attached, or 100, or a -6, right, or a pi. You don't know anything about it. So every time when you integrate something, you will just put plus c and walk away, unless additional information is provided and you can compute plus c. But again, more on that at the end of the class today. Now, the argument here is that you already know all of the basic integrals, because all of the formulas for integration are backwards formulas from derivatives. So, what are the formulas that you must know / already know? You know that derivative of a constant is 0. You read that backwards. Integral of 0 dx is going to be some constant. Now that's your plus c, right? integral of a constant k is kx plus c. Very good. You will have the plus c every time. Why is this an integral? Because if you differentiate this function, derivative of x is 1, derivative of a constant is 0, so you just have k. Woohoo! Integrals are really cool because you can always check if you care. You just differentiate the answer and you must get what you integrated. Otherwise, your problem is wrong. So even though it's much harder than derivatives, I always liked integration better. Derivatives you can check, right? It's just you hope you got it. But for integrals, 100% of integrals of Calc1 and Calc2, if you care, you can take the derivative and check that you integrated correctly. And then there might be extra steps to do that in a problem, but at least you know you integrated correctly. It's like you have a 60% of the credit in your pocket, right? If there is more stuff to be done. All right, next one is the one that looks different. X to the n. So this is, again, a lot of those x squared and all that kind of stuff. New formula, guys. This is the one that you will have to memorize from scratch. X to the n plus 1 over n plus 1 plus c. What?
Dude, don't be weak.
Good. Good ones. Even though we're missing the last two. All right. He started laughing, so he lost. Guys, this particular formula covers 3 different types of functions. X to the n could just be x to the 6th power. So if you have integral x to the 6 dx, then you just have x to the 7 over 7 plus c, and you walk away. Your n was 6. 6 plus 1 is 7. Just populate that everywhere in the formula and you are done. So it works on polynomials. But you also can have the integral of cube root of x dx. So now that's a radical, because you can rewrite this using algebra as x to 1/3 dx. And now when you add 1, you get 4/3. So you will have x to the 4/3 divided by 4/3 plus c, and this would be radical. Radical functions are also in the same formula, just like your derivatives. And finally, you could have integral of dx over x to the 4. You can rewrite this as integral x to the minus 4 dx, which is x to the minus 3 over minus 3 plus c, rational. The same rules you had for derivatives, one formula to deal with these 3 types of functions. Over here you have, again, the same formula deal with the same functions. Cool. What are other formulas you know from derivatives that you can just make into integral formulas? Trig, let's go e to the x first, and then we will have 6 for trig, yes. So e to the x dx is what? E to the x plus c. You either have a plus c or a minus 1 on the test. for every plus c you miss. So, yeah. Now, in general, you are not going to see e to the x, right? You're going to see e to the ax, e to the 3x, e to the 5x, right? So I'm going to put that purple over here. E to the ax dx is e to the ax divided by a plus c. If you remember the derivatives, it was a times, right? Now it's divided by a. So that one will be there most of the time. As I said, e to the 2x, e to the 3x, e to the 6x, right? That's what's there. Okay, now partner in crime. Integral dx over x, also known as integral 1 over x dx, is what? Derivative of what would give you ln? Nice. Except now you have to be very careful. Your ln must have absolute values around. And I'm going to explain that one right away. These absolute values are not optional, they must be there. Now, let's see why. I'm going to erase all of this as just explanation why. You might not care, but here we go. If you have function 1 over x, its graph is this, which means that the domain is negative infinity to 0 union 0 to infinity, and you can say x equals, let's say, negative 2. If you just have ln x without absolute values, your graph looks like this. Your domain is 0 to infinity, and you cannot pick negative 2. Now, when you have an equal sign between left side of the equation and the right side of the equation, you better be able to feed the same numbers, right? In order for stuff to be the same. Make sense? So, when you put absolute values around x, it spawns another branch like this, and that brings in negative infinity to 0, and now domains on both sides are the same, so you can feed the same numbers on the left side and on the right side. That is very important. Derivatives don't have it. Derivative of ln x, no absolute values. Derivative of ln x is equal to 1 over x, and you're done. For integration is opposite. You feed in, you cannot have more restrictive domain for integration because application later on will show that integrals calculate area under the curve. Guys, if I'm calculating area under the curve, I am cutting away half of the area, right? And when you make a mistake by a half, like imagine if the half of the bridge is missing, right? The other half is there, but you know the other half is missing. I guess you pay half of the toll in that case or something, but right? So again, absolute value is not optional. You will be penalized for it if you miss it. Make sure you know that. So must have absolute value. And now, by popular demand, we have our 6 trigonometric functions, and then 2 inverse trig functions. So once we write these 8 formulas down, we are done with basic integral chart, right? Which is your derivatives backwards. What is the integral of sine x dx? Negative cosine. That's the boss move right there. Derivative of sine is positive cosine. Integral of sine is a negative cosine. Why? Well, what's the derivative of cosine? Negative sine. And this negative makes it a positive, right? Yeah. So derivative would be negative sine x, and now that's a sine x, and you see that's the same. So, make sure you know that. Now, what would be the integral of cosine x dx? Positive sine x plus c. Nice. Awesome. Is integral of tangent dx basic integral? No. Because you do not have a function whose derivative is tangent. You take derivative of tangent to get mass, but you do not get the derivative of something to give you tangent. So we do not have integral of tangent, cotangent, secant, and cosecant as basic integrals. We do have them, but they're Calc2 business, okay? We have the integral of secant squared x dx as a basic integral, and that is tangent x plus c. We have integral of cosecant squared x dx as a negative cotangent x plus no cofing c. And the last two for trig are integral of secant x tangent x dx, whose integral is secant x plus c. And finally, integral of cosecant x cotangent x dx to give us negative cosecant x plus c. There they are, your basic integration. Are you memorizing this? Hopefully not. If you know your derivatives, derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. Derivative of secant is secant tangent. Do you see that? So if you, on your test, write your derivative formulas, just read them backwards for integrals. The minus signs and everything else is just going to jump to the other side. Okay? That's all it is. Just reading derivative formulas backwards. And now we get to the inverse dx of 1 plus x squared, which is listed as inverse tangent of x plus c. This one appears in Calc2 and differential equations a lot. I told you gotta know the derivative of inverse tangent. This is why. No one cares about the derivative of inverse tangent ever, right? We only care about the integral of the form that will give us inverse tangent. Some of our solutions to something called partial fraction decomposition is going to land here very frequently. So we need to know that one. We actually need to know the purple form, you know, the one on steroids. dx over x squared plus a squared. See, I'm not using I'm not using the 1 anymore. It's now a squared. And the answer for this is 1 over a inverse tangent x over a plus c. That's the one. So these purple formulas are the ones that are there frequently, just like the one for e that you had. And we're just going to have one more for inverse sine. We really don't care about the other four, all right? We just care about inverse sine and inverse tangent, technically, because they're the ones that show up. This one is the derivative of, what do I want? The integral of inverse sine. So 1 over square root of 1 minus x squared, you can put dx on top, right there, is going to be inverse sine of x plus c. And this is it. The only new formula that you haven't seen before is this one. Everything else is to the letter backward derivative you learned in chapter 3. All of it. Now we're going to have some very important properties. Yes?
Is there a purple thingy for the sign or no?
There is.
So we need to know.
Yeah, it's a squared minus x squared, and you get 1 over a and x over a. So if you put a squared over here, you will put 1 over a and over a again. But again, it's rare. Plus, there is something in Calc2 that you would be using to deal with this. It's called trigonometric substitution, where you take the normal looking integrals with x squared and so on and turn them on purpose into trig. That's why it's called trig sub. You are subbing trigonometric functions for these ones to make the integral possible. It's going to be epic. Properties of integrals. These are not all properties of integrals. These are the most important ones. Again, in blood. If I am integrating two functions, f of x plus g of x, I have to put them in parentheses because they are multiplied by dx. This dx that is just there all the time as a notation will have a big purpose in terms of application and area and so on. It's not there for decoration. You must have dx. And because that dx is multiplied into functions, if you're adding two functions, you have to put them in parentheses. Now, when you have addition of two functions, they break as individual integrals for each function. So if I have square root of x plus x cubed, well, that's just two separate integrals, right? That's we say term-wise. You are integrating term-wise. Every term is its own problem. And you keep, as you will see now in the next case here, you keep the signs, whatever they are, because the next one is f of x minus g of x times dx, and that's going to be integral of f of x dx minus the integral of g of x dx. The last property, integral of c, not c, k of f of x dx is k integral f of x dx. Just like the limits, just like the derivatives, you can kick the constant out and not worry about it. So if you have 3x to the 7, you kick 3 out, you deal with x to the 7 by plus 1, right? And then that 3 is copied. So now we're going to do 5,000 examples. This is it, apart from looking what is the plus c, right? But we covered the entire list of all integrals, which are basic backwards derivatives. And the three properties, which these are the properties of linearity. You'll learn that in linear algebra. And these properties simply say you can work on each term separately. So now, what kind of a problem can I work on? Well, maybe I have integral of 4e to the 2x minus x to the 8 plus 6 dx. So if you are supposed to, right, you're supposed to integrate. You have three separate problems because you have three terms. So there will be a first one is 4 integral e to the 2x dx. You kick 4 outside. It's a constant. Kick it outside. Minus integral of x to the 8 dx plus integral of 6 dx. All right. Copy 4. And if you use the purple formula for ease, you know that this is e to the 2x over 2. E to the 2x over 2. Now we still have 3 to go. Minus x to the 9 over 9. Right? It's plus 1, right? And plus, what's the last one? 6x, very good. 6x. And now you put plus c. Plus c for the whole problem. You might have a plus c1 for the first, and plus c2 for the second, and plus c3 for the third one. But then you mush them all into one plus c at the end. There is no reason to have 3 separate plus c's. We can cancel 4 and 2 and just get a 2 over here. And we're done. So now, if you want to write nice, you can also put 1 over 9 times x to the 9 as a coefficient. And you walk away from the problem. That's it, done. What did you just say? You don't believe me? Differentiate. Differentiate. Go on. What's the derivative of e to the 2x?
4 e to the 2x.
Yeah. And what's the derivative of x to the 9? 9 x to the 8, but that 9 will kill off 1 over 9, right? Right. And what's the derivative of 6x? 6. It's exactly what we have here, right? So think twice to challenge me next time. I'm heavy. All right. Actually, now that we are at the...
Just kill it.
Well, it's one slice, but still. You can stretch it. Maybe some civilians would like more. I don't know. Anyway. Ooh, this is going to be 9 divided by 4 cube root of x squared and dx. It looks terrible. But you know exactly what to do. Maybe. I'm busy.
That's a big maybe.
Well, what is the thing we don't have to worry about? 9 and what else?
4.
And a 4. Is that a 9 over 4 constant? Okay, kick it out. What's left?
dx over the cube root of x squared.
All right, now you know that dx. I'm busy. Right on the side. Convert the exponent. Let's go. So, what algebra voodoo do I need to use here to write this as x? To the negative 2/3. Excellent. Do we see that this is of the form x to the n? Use the formula for x to the n. Nice one. And then fix your fractions. Now let's say you care. You will differentiate the answer and you must get this. Right? So let's go. What we got? Copy the constant, 27 over 4. Derivative of x to the 1/3 is 1/3, x to the negative 2/3, and then plus 0. These guys cancel to 9 over 4. X goes downstairs as cube root of x squared. And there you go. That was exactly what was in a peanut. Awesome. You can do very well with integrals, which means your first half of Calc 2 is a joke if you check your answers and get comfortable with which formula goes where. Now, that being said, can't leave without doing any trig. I mean, right? Right. So, what is the integral of 6 secant squared x dx? Kick out the 6. Very good. Yes. 6 tangent x plus c. We move along with our lives. Now, you know how there is a purple formula for e and a purple formula for inverse tangent, and there are purple formulas for all 6 trig functions. Let's just do one in purple. What is the integral of cosine of 3x dx? And the answer is, integral of cosine is?
Sine.
Positive sine. Very good. So it's just going to be sine 3x divided by 3 plus c. So you see the pattern that for purple formulas, if you have a number in front of the x, which is the argument, right, you will just have divided by that number. That was that over a for inverse tangent, over a for e to the ax was over a. Now you have an over a for all 6 trig functions. So let's say you have integral, write it down, integral of cosecant 5x cotangent 5x dx. Cosecant 5x cotangent 5x dx. Anyone? Yes, I heard 3 of you said plus c, which is more than I'm used to. So that's great. Right now, guys, this plus c is -1 when you don't put it in the problem. When you get to differential equations, plus c missing kills half of your problem. It's huge later on, okay? Huge. So do we feel comfortable? Somewhat? I want to go back to my integral of 2x equal x squared plus c. So we saw some integrals. We know we can check with derivatives. All cute. You're going to look at those formulas. Right? Life is good. Going back to the idea of integral of 2x dx is equal to x squared plus c. Those of you who paid attention in pre-calculus 1 know that when I add or subtract a number at the end of the function, shifts. Yeah, which way? Good. Up and down. Excellent. So, what do I have as a graph of this function? I have the infinite stack of x squares. There is the one that goes through this, but then there are infinitely many of them going this way and infinitely many of those going down. Each one of these is going to be a value c, 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 infinitely many c's. Every single one of those y-intercepts. And what they do is they just, go up and down, up and down, up and down. This is what we would call general solution. In general, solution is x squared plus some constant. If you want the particular solution, the solution, the function, you are going to be given a point on a side. So, if you are given something that is called initial point, or initial condition, both of these are used. If this is given to you, you can compute value of c. So let's say initial point or initial condition is given to you as, say, um, 753, whatever. Put whatever, doesn't matter. So let's say that's given. That 753 is somewhere on this graph. Let's say 753 is here. If that point is 753 on a graph, that means that this particular line with this particular C is the line, and the rest of them don't count. This is what allows you to compute the C because it went through particular C. So now what you have? You have that your function y equals x squared plus c, and over here you have that x is 7 and y is 53. It's a joke to calculate c, right? Just plug it in. So 53 is equal to 7 squared plus c, c equals to 4. And now I have x squared plus 4 as the function that we are looking for. So if you are given this initial position, initial condition, and that's always a point, x comma y, You plug in the x, you plug in the y, and you can calculate c. Generally, they are 0, 1, 0, 2, or 1.5, 5, right? I picked 753, doesn't matter what you pick, right? Now, obviously, when you do application, it matters, right? The project for Calc2, since Thanksgiving, they're baking. Now, they have to do separable differential equation for chapter 9, and when they take a temperature of whatever they're baking, they can do chicken, they can do ham, they can do turkey, cookies, I don't care what they're baking. With a temperature probe, 30 minutes into baking, temperature is going to be 92, let's say, right? So they're going to have a data point 30, 92. That's that point, all right? And with that, they will be able to calculate C, which gives them the constants of the oven, and right, and then they can calculate the exact time down to a second where, let's say, turkey or chicken is going to reach 165 degrees. You calculate that down to a second, set the timer, go play video games, all right? When the timer goes beep, you just take the thing out and it's done. There's no reason for you to cut inside and check or anything like that. Because if the Newton's law of cooling, which is what they have, which in differential equation, that's the next semester for you guys, calculated, right, that is going to take additional 1 hour and 7 minutes, then you put the timer on 67, and when you come back in 67 minutes, the temperature will be exactly 165, and that's done and done. Now, that one measurement point, 30 minutes into baking, provides you in this point, and that point calculates C, and in differential equations, I told you it's half of the problem. You don't get to mess with plus C in DTQs. You forget it, you're done. I mean, your problem is done. So get in the habit of writing plus C every time you solve the integral. We'll upgrade later. And that's 4.9. Introduction to integration. These formulas will stick with you forever now, all right? Calc2, Calc3, differential equations, thermodynamics, right? Whatever course, electrical engineering, pretty much every course you ever take, you take electrical circuits, you're going to do couple differential equations for Kirchhoff laws for loops, and there will be differential equations for current and voltage and all this kind of stuff. Integration will never go away. And the goal of chapter 5, first 2 sections, is to show the application of integration. Chapter 3, section 3, to give us a little bit of a theoretical. Section 4, 3 formulas. One is cool, like one of those formulas is the average formula. So we're going to have the mean value theorem integral form. That's kind of cool. And then the most important, right, like section of Calc1 if you are going to Calc2. 5 U substitution. About 90% of your integrals are going to be U sub in your Calc2 course. Your first exam is all U sub. Second exam, 1/3 of exam was U sub because you had other 5 integration techniques. U sub always remains the most important and most used integration techniques, which is 5 because it's backwards chain rule, which makes sense. If most of your derivatives in life are chain rule, then the most used backwards technique, antiderivative, has to be the backwards chain rule, which is called U sub. And that's one of those 6 sections, but this one pretty much is, you don't learn 5 well, then Calc2 is hell on earth, right? Hell on earth. So now you've seen entire chapter 4. It was application of derivatives and this excursion right into integration, this little right vacation that we had to see all of the backwards, right? When you read derivative formulas backwards, we get integrals. And the problems, right? Sometimes now when you solve these problems, you have to be creative with algebra, right? If you have a problem that looks like this, it says integral of 3x squared minus x to the 9 divided by, let's say, 6x to the 4th dx. Right? When you see something like this, if it's flipped, you can't do it. You have to wait for Calc2. Now you can. What are you supposed to do? Separate them. Your minus sign is in the numerator. The two fractions can split. Each one gets its own integral. And then you do the algebra to deal with the powers. And then you do the problem. So you split kick the constants, deal with powers, and now you have your basic x to the n integral. Are we green there? So you are looking for algebraic manipulations to get you into basic integrals. You do not have any of the... Is there a product rule for this? Yes, in Calc 2. Right? Calc 2 chapter 8 is when you see the product rule for integration. So right now you are dealing with basic addition and subtraction between the terms. You are looking for the basic splits. It's not going to be anything crazy, right? So don't read too much into these things. We have 1/2. What?
Could you take a second integral?
You mean integral of the integral?
Yeah.
Yes. That is exactly what we are going to do eventually, because you are going to have your acceleration. You are going to integrate and get velocity. You're going to integrate and get the position function. So you can do nested integration, and you can do nested integration across dimensions. Welcome Calc 3. So it's going to get very interesting, and you will laugh at this stuff when you get there. Because right now, everything is new, everything is fresh, everything is threatening, right? But, yeah. But when you get there, you're like, it's Calc 1 problem 3 times. What's the integral of x to the negative half?
1 over x.
X to the negative 1 over negative 1, good. Minus 1 over 6. X to the 6 over 6 plus c or minus 1. And now we have negative 1 over 2x. Are we all bueno on that? Minus 1 over, x to the 6 over 36. We bueno there? Plus c.
So it's impossible to take the integral of x to the negative 1.
No, it's not.
It's not? But you can't take the derivative of that, because that would just go to 0, wouldn't it?
It takes me so long to scroll to it, but I got it. Yeah, LN plugged it right in. Like that one issue, right? Right? If you have x to the minus 1, when you add 1, you get x to the 0 divided by 0. That's a problem for that formula. Well, luckily, ln plugged that issue right up for us, right? So woohoo for ln. Excellent. Excellent question. So all of your polynomials x to the n work except n is -1. Well, when you have -1, it's ln. Cool? Of course, cool. It's calculus. All right, what else? Any other questions, concerns? No? Let's take a break then and then peek into chapter 5. See what's cooking. Bye.